Hello, this is Stephanie Rawls, and today I will be presenting my findings from Lab 2. Like in Lab 1, the fundamental principles is the same, where we observe the conservation of charge and Coulomb's law for calculating electric fields and electric force. However, the difference here is that in our computational model, we modeled our tapes as continuous lines of point charges instead of just one point charge. From Lab 1, I found the mass of the tape to be equal 0.0002 kilograms, and the separated distance between the floating tapes to be 0.0175 meters. As in the last lab, we used several equations such as the force equation as well as the electric field equation that is shown below. We will use the exact same in this lab, except it will apply to several point charges that are aligned in one line instead of just one point charge. Some major assumptions in this lab include that we ignore air resistance as a force. We assume that charge was evenly distributed across both tapes. We modeled both the tapes as a series of point charges instead of one point charge. And we also assume acceleration equals 0. From previously in Lab 1, we used our hand calculation to find our charge, in which the equation is presented. We found that the charge was equal to 8.1 times 10 to the negative 9th coulombs. However, using the computational model in our new lab today, we found that the charge was equal to 2.035 times 10 to the negative 8th coulombs. Some major parts of my coding, going from left to right, includes establishing my initial values, such as the mass, the charge, as well as the distance between the floating tapes. Calculating the E field between the two tapes using our electric field equation K times Q divided by the magnitude of our observation location squared times R hat. Next was setting up the line of charges with at least 100 points for both the bottom and the top tape. And last, setting up the scale so that our model can show our arrows for our forces and fields. Here's the comparison of the two models. We see the new model accounts for the electric fields emitted by each point charge on the line to calculate the electric force and the electric fields of each. However, our old model simply accounted for one point charge that was heavily concentrated with all the charges and placed in only one location. We also see that with our new model, there is slight changes in direction as we move in toward the middle of the line. These slight changes describes behavior of the charge better than the old model, as we can note that the one charge on the top feels the attraction of other charges by the bottom charges as well as those that neighbor it. To close the presentation, we may ask two questions. What if we kept the same model from Lab 1? And what is the difference between the point model and the line charge model? I answered with the line charge model computed a much smaller magnitude for the charge, while the point charge was much larger. This is probably due to the line charge accounting for each location of the points that make up the line. With this, we have a change in direction that affects more of our electric field and makes it fluctuate due to different negative direction and overall values. The next question asks, why do they differ? Which is more accurate and why? As stated before, they differ due to the line charge accounting for the location of each single point on the line. The line charge is more accurate as it accounts for the different locations on the tape and not just one single location. As we discussed in class, the model is basically using an integral to calculate the charge in the entire line charge, in which it calculates each section's charge. From there, it adds up all the small fields to find the entire E field of the entire line. On the other hand, the point charge only accounted for one single point that interacted with another single point at one single location. Thus, we have no fluctuation in different directions. It is only up and down. That concludes my presentation. Thank you for listening.